All right, I think we're going to go ahead and get started. Happy Halloween, everyone. Cool, so today we're talking about the second half of constraint satisfaction problems. Oh, the mic's not on. Okay, good point. Mode? Hello? 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 How about now? Oh, okay, it's working now. Great. Okay, cool. So yeah, today we're talking about the second half of constraint satisfaction problems, where last lecture, if you remember, Percy talked about how to deal with constraint satisfaction problems where you have hard constraints, and today we'll be thinking about soft constraints, where we'll see what that means very shortly. So let's start with a review of what the setup is. So the big object in the constraint satisfaction problem lectures is this factor graph, the most important thing. So what's in here? The circles are variables, so they can take on different values. And the factors are functions which take in those variables and output a score about how happy they are with a particular assignment of variables. So the factors are these little squares down here with labeled f. And the edges, what they're connected to, those indicate the variables that they depend on. And then just to review some notation here, domain sub I for x sub I, those are all the values that the variable x sub I can take on. So domain might be something like if x can be a color, it can take on some color. Domain sub I would be the set like red, blue, and green. Okay. Cool. And then just as I said, factors. There are a set of factors here. And the factors take in the entire set of variables, but really they only depend on a subset of them. And they output some score, which has to be positive. And the set of variables that each factor depends on is called the set of dependent variables. So f1 only depends on x1, f2 only depends on x1 and x2, and so on and so forth. All right, so I think we saw this picture of a factor graph last time. Here's a concrete example of a factor graph. Let's suppose you have a bunch of people, and they either prefer blue or red. And we have this knowledge, this prior knowledge, that the first person must agree with the second person, and the second person tends to agree with the third person. So we can model that as a factor graph. In this case, each variable x represents one of the people, and the factors encode their ability to agree with each other, as well as their own personal preferences. So f1 here is only a function of x1, and it tells us that it is only happy if x1 chooses blue. So this is saying that the first person has to have blue. If you pick red for the first person, he's extremely unhappy, and we'll put 0 for the overall weight. Likewise, f2 here. So the way to read this table is the first column is the value that x1 takes on, the second column is the value that x2 takes on, and the third column, f2, is what this factor thinks of this particular assignment of the variables. So it's quite happy when they agree on red. It's quite happy when they agree on blue, but it is unhappy when they disagree, which is why it gets 0. And we can look at the other factors, which have very similar information. In this case, this factor doesn't actually assign 0 to any particular combination, but you can tell that it likes certain combinations better than others. And finally, we've got another unary factor, which only depends on x3, which says that the third person slightly prefers red a little bit more than blue. So hopefully that reloads some context about how these factors work. Great. So the overall score of a factor graph, once you've assigned all the variables, or let's call it a weight, is just the product of all the factors. So if you remember from last lecture, if any factor has a 0, as its value, then this whole thing will be 0. So it has the ability to veto the entire configuration. No matter what you do on the other factors, if one of them is 0, the whole thing is 0. So that's a property of the product. And in this lecture, the main objective that we'll be interested in is finding an assignment to the variables that maximizes this weight. So in the previous lecture, it was much more about finding an assignment that didn't get us 0. Any assignment we could get that didn't violate one of the constraints that got a non-zero value was good. In this lecture, we're actually thinking about maximizing the weight. not just finding something that's non-zero. Any questions about that basic setup? All right, cool. So we saw that this sort of constraint satisfaction problem could be formulated as a search problem. So in our usual search tree, we've got a root node that we start with, where maybe none of the variables are assigned, or maybe some of them are assigned. And the actions in this space is to take one variable and assign a value to it. So one action, for example, here might be to set the variable q to red. Another action after that we could take is set the variable nt to green, and so on and so forth until we hit, oh, the zoom is off, until we hit some leaf node of the tree. And a leaf node corresponds to a factor graph where all the variables have been assigned. And we can use the backtracking search procedure that we've seen a lot of times at this point to go and iterate through the entire tree and find all the leaf nodes inside this tree. And a simple algorithm then is to look at all the leaf nodes, look at what score each one of them got, and just return the one that had the best score. So that's a brute force procedure where you literally try every combination. Okay, so the complexity of that is not very good. Let's parse this expression up here. So the backtracking search procedure we just described has this time complexity. Domain here refers to the set of different values that a variable can take on. So in the previous example, it was red, green, and purple, I think. So the cardinality of that domain is 3. And in the previous graph, I think there were 7 variables. So the complexity here would be 3 to the 7. And you can tell that as the number of variables increases, that blows up very quickly. So that's not good. Last lecture, Percy talked about various ways to prune down that search so that you could preemptively realize that certain variables were just not going to work out in the long run because there were no satisfying assignments later for the other variables that you hadn't filled in. And that was called forward checking and more generally AC3. So despite pruning a lot of things, the worst case complexity is still exactly the same. And that's not good. Another part of last time's lectures was to explore different ways of ordering the way in which you choose variables. So which variable do you actually choose to set a value to first? And when you set a value, which value should you try setting it to first? All of those heuristics also help you find a satisfying solution more quickly. But at the end of the day, the order complexity is still the same. The worst case is still the same. And the last thing that we'd like to improve on from last lecture is that none of these pruning techniques actually work when you have a graph that doesn't have any constraints in it. So if none of the factors actually produce 0, all of these heuristics don't really do anything. They're designed to stop early or fail fast when they encounter a 0. So if I'm in a factor graph where I need to find the highest value configuration of the variables, but no factor gives me a hard no, then none of these work. I still have to search over all of the configurations naively. So this lecture will be about how we can actually search over factor graphs for a good assignment where there aren't hard constraints. Cool. So as an example for this lecture, a running example, we're going to be thinking about object tracking. So in object tracking, suppose you have a camera and you're taking pictures of some object moving over time, and you only see frames every once in a while, and you want to recover the true path that the object took. And suppose maybe that each frame is very noisy, so you don't get a precise estimate of where they are. Let me do a whiteboard picture of that. Okay, so let's say this is time. This axis is time right here, time t. And we're observing an object just on one dimension, just to keep this picture easy. So let's say that an object kind of walks over time from the bottom up to the top. So time 1, maybe it's here, time 2, it's here, time 3, it's here, 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 and so on. So that might be the trajectory it takes over time. But maybe we have some noisy sensor that doesn't get a very good estimate of where they are. So the sensor maybe reports that they're here at this position, and then here, and then here, 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 and here. So when you look at this, you're thinking, well, there's no way that this person is jumping that much in between each time step. They can't be kind of teleporting from here to here and then back up. They can't move that much each frame. So you'd want to apply some sort of smoothing constraint to say, after every time step, they shouldn't be able to move that much. And we're going to be able to formulate this as a factor graph. So let's look at how that factor graph looks like. All right, so this picture up here features only 3 time steps. So x1 is the position of the person at time 1, x2 is the position of that same person at time 2, and x3 is their position at time 3. So what do these factors in between these variables represent? All right, we already said that. That's what the variables are. And we're going to have 2 kinds of factors. So you'll notice that there are unary factors hanging off each variable, O1, O2, and O3, hanging off of x1, x2, and x3. Those are the factors that say the person should be close to where I saw them in the picture. So that factor is very happy if we assign a value to x1 that is close to the actual observed place we saw, x1. O2 is very happy if x2 is close to where we observed it. So in other words, these blue dots are the values of x1 that I'm trying to figure out. So suppose that I don't actually know them, and my observations are these red checkboxes. So the factor O1 is quite happy if I put the blue dot here, but it's going to give me a very small value if I put it farther away from the red x. All right, so those are the first factors. And then the second set of factors are the ones that relate x1 to x2 and x2 to x3. And those factors will essentially have a high score when x1 and x2 are close to each other, and a low score when x1 and x2 are far apart, to impose this sort of smoothness condition that a person shouldn't teleport very far from where he was or she was at the previous time step. Okay, any questions about the setup of that factor graph? Yes?
For the factors O1, when would they take a high value, and when would they take
a low value?
A low value.
Okay, so the factor O1, let's say, or let's look at O2. Let's look at this point right. Let's just look at this point right here. If I set x1 to be exactly on top of the observed position, then the factor is as happy as it possibly can be. And as I move it farther away, the value you can imagine it decaying to 0. Yeah. All right, so let's actually look at what this looks like in code. I'll zoom in here. So there's a lot on this page. I don't want you to look at everything right now, except just look at what I'm highlighting inside this box here. So the first thing we're going to do is define a set of variables. Let's zoom in some more. Okay, so you can see here that we've defined a variable x1. And what this is saying here is that there are 3 possible values that x1 could be. It could be 0 or 1 or 2. This is the position that person 1 is at. x2, the same. They could be at these possible positions. And x3 could be at these possible positions. So then, all right, now we want to define the 2 different types of factors, T1 and sort of the T factors and the O factors. So the transitions we're going to define below. Let me break this up a little bit more. So actually, maybe this is better. So here we have this function nearby, and it takes 2 values, an A and a B, and it says that if A and B are equal, then return the highest score 2. And if their difference is 1, return 1. And then if it's anything else, if it's anything farther away, return 0. So that gives you that decaying sort of, if you're far away, give lower scores type behavior. All right, so that was just a helper function. Now we actually look at this observe function. And this observe function represents the factor O that I was talking about earlier. So it takes a single variable as input, and it says, or rather, okay, so ignore this variable right now. This is actually the location that is observed. So that's A. And this B is so this function actually returns a subfunction inside of it, and it's this that's actually the observation factor. So I know the notation is a little bit unclear here. But once we look at this function here, what it says is, I'll take some value, B, and if it's near A, I'm going to give a high score, and if it's far away from A, I'm going to give a low score. So now we construct this factor O1 by saying that the factor should impose that x1 should be close to 0. So if we saw an observation at time 0 that the person was at time 0, this factor will be happy if we set x1 close to 0. Then if we look at this factor right here, it's saying we'll be happy if the variable x2 is set close to 2. And likewise, we'll be happy if the variable x3 is close to 2. And these other factors right here, factor t2, takes the actual nearby function that we defined earlier, and it says if x1 and x2 are close to each other, I'm happy. And this one says if x2 and x3 are close to each other, I'm happy. So I'd be happy to clarify sort of the details of this code later, but I just want to give you the general impression of what the code looks like. Any questions about that so far? OK, so the actual graph that's defined by this code over here is right over here, which is the same one that you saw in the slides. And the observations that we've passed in are 0 at time 1, 2 at time 2, and 2 at time 3. So if we go ahead and run this, we can get what the optimal configuration for this factor graph is. All right, so go ahead and do that. And ignore most of this output for now. The only thing that you need to pay attention to right now is the final output from the algorithm, which is this line right here. So we can see that x1 gets set to 1, x2 gets set to 2, and x3 gets set to 2. And the overall score for this is 8, which is higher than any of the other possible configurations. So the result you get is something that's a smoothed out version of the original path. OK, so we just went over the basic running example that we'll be using throughout this lecture. And now we can actually look at some of the methods that we'll be using to find the maximum weight assignment in a factor graph. The first one we're going to look at is beam search. So let's see how that looks. As we already discussed, the way in which you actually fill out the values or assign values to every variable in a factor graph is a search process. And that search process can be represented by a tree. So just to help you ground this picture, each edge in this graph, in this tree, is the assignment of one variable to a particular value. And the depth of the tree is equal to the number of variables that you need to assign. And that should make sense, right? Because if you're filling out all of the variables in a factor graph, you need to take one action to do that. And the number of actions you take is the depth of that tree as you traverse down. OK, so instead of exploring the entire tree, a simpler thing you could do is just do a form of greedy search. So rather than considering all of the options, I start at the root, and I look at which action looks best among the immediate actions that I can take. So in terms of the factor graph, what this is saying is I'm going to pick one variable, and I'm going to assign the value that is best for just this variable. In other words, I'm only going to look at the factors that are connected to just this variable and not the others. And I'll pick whichever assignment looks best. And once I've done that, I'm going to never consider the other options ever again. I'm just going to fix the value of this variable to that value. So that corresponds to only going down one side of the tree. In this case, we've gone down the right side. Then at the next stage, I get to assign another value to the next variable, and I do the exact same thing again. I pick one assignment that's best and continue onwards. So if we keep doing this, we eventually get to the bottom of the tree, and we've got a full assignment. But it definitely has not considered all the other possible options and assignments that I could have taken. So this doesn't necessarily give you an optimal solution, but it's definitely a fast algorithm, right? So the number of actions you take is just proportional to the number of variables that you have to fill out. And one quick thing I should emphasize is that when I'm deciding which assignment to take, I'm considering the entire weight of the graph that I've assigned so far. So I'm not just looking, like when I get to this node right here, I'm not just looking at the factors that are attached to that variable. I'm looking at all of the factors that participate in all of the variables that I've assigned so far. So in some sense, I'm using kind of my partial estimate of the entire factor graph score to choose what to do. OK. Cool. I will skip over this demo really quick because we'll see something slightly more general in a second. So let's describe this formally. We start with a partial assignment of all the variables. In this case, we start with the empty assignment. So x is just no variables assigned. And then what we do is we loop through all of the variables. So for each I equals 1 through n, let's say there are n variables, we loop through them one at a time. And for each one, let's look at this notation right here. So x is all of our assignments so far. And this is saying, add to that assignment the fact that xi I'm setting equal to v. And then we take that assignment and compute its weight. Once we've done that, we consider all the different v's that you could have set xi to, and we pick the v that had the highest weight. And then we repeat that process for every variable. And that's greedy search. Question over there.
Are we assuming that there is no factors that return weight 0? Because it seems like if there were a factor that could return weight 0, you could just find a dead end at one point. Like you could find yourself in an unstable or like invalid configuration.
Yeah. So the question is, are we assuming that there aren't any factors that return 0? And the answer is, this algorithm will bullheadedly keep going even once it encounters a 0. And the solution it finds at the end is just going to have a value of 0. So it has no way of recovering, even if it makes a mistake. Other questions? OK, cool. So beam search is going to be a slight generalization of greedy search. In greedy search, you look at your one best option at every time step, and you keep extending that. What beam search will do is actually try to hold on to more than one path and extend multiple paths simultaneously. So I think maybe a picture is the best way to show this. All right, so in beam search, there's a parameter k, which is the beam size. And that you can think of as the number of paths it can keep track of at once. So let's say that k equals 4. All right, so we take our original node, and we have two different actions we can take. And they both look pretty good. And because our beam size is 4, we can actually just take both directions. So we go down the left and we go down the right. Once we've done that, the left and the right both have 2 more options each. So we have 4 different paths now. One that goes kind of, if I trace it with my mouse, there's one path here, another path this way, and another path that way. So 4 paths. Again, we have a beam size of 4, so we can keep all of them. For each of those, we extend them. And now that we've extended all of those, we actually have 8 different paths, and we can't hold on to all of them. Because if we hold on to all of them, then we're just going to get that exponential blow up again of backtracking search. So here's where beam search does something differently. It looks at the scores or the weights of all 8 of these paths, all 8 of these partial assignments, and then it keeps the top 4 highest scoring ones. So it's still kind of greedy. It's saying, I haven't figured out the whole problem yet, but given what I know right now, these 4 are the best, and I'm just going to keep these. And the other 4, I'm just going to stop exploring them. So the bolded lines are the paths that we're going to take, and the grayed out lines are the ones that we're not going to take. So we keep the top 4. Again, those top 4 spawn more paths. Again, we take the top 4 of those, and we keep going until we reach the very end. So at the very end, you can see that we only found 4 solutions. And another thing you might want to note is that certain paths after the pruning process have no descendants. They completely just fail. All of the descendants might actually end up down a single path in the beginning. So it's not that every path you started with has to keep getting extended to the end. They can be pruned away completely at different stages. OK, so let's give a quick demo of that. All right, so the way that this demo is going to work is it's going to assign x1 first, and then it will assign x2 and then x3. That's the order in which it will go. Let's start with x1. So x1 has 3 possible values. It can take on 0, 1, or 2. The red value indicates what value we're considering for x1, and the black value is the weight of the overall assignment so far. All right. Let's step through this. Okay, so we keep the top 3. In this case, our beam size is 3. So we can keep all of those different assignments. And now, now this is where it gets interesting. So let's zoom in on this a little bit. You can see that we're building out a tree. This is the, so if we look at this, we can see various paths that form here. And here we see a path that goes from 0 to 2. So what is that saying? That's saying we assign 0 to x1, and we assign 2 to x2. Likewise, this path right here says that we assign 2 to x1, and then we assign 2 to x2. And at the very end, we see the score for having taken that path. So a lot of these scores are 0, because as someone mentioned, certain assignments just get a value of 0. And of these, we see that some of them get 2, and incidentally, there are 3 of them that get 2. So beam search will prune away everything else except for the ones that get 2. And we'll see that after I update this here. Okay, so that prunes away all the paths that have lower scores. And then again, finally, we go to assign the third variable, get some scores, and prune away the ones that are smaller, leaving us with these. And once we're done with that, we just look at our remaining solutions and pick the highest one, and that's how we find the best assignment. So this is still an approximate algorithm because we can potentially miss solutions that look bad early on but turn out to be the best later. Okay. This algorithm basically says what I just described in more formal notation, so we'll skip over that for now. Okay, so what is the running time of this algorithm? We said that backtracking search was very bad. It has exponential time. The running time of this is the following expression up here, and I'll parse that for us. So first of all, let's look at the n in the expression right here. So n is the number of variables. And the reason there's an n here is because we're going to repeatedly assign variables n times. So that's where the n comes from. And each time we assign a variable, you have to think about what we're doing. So we're looking at all of the paths that we've extended, and then we're sorting them by order of their score and picking the top k. So the sort procedure, as you know, like if there are d elements in a set, then the sort is d log d, right? The number of things that we're sorting at each step in this case is k times b. So why is that? Let's look at this picture really quickly. So if you notice here, at a given level, we had k things, right? Because beam search allows us to keep k things. And then the branching factor is b. So when we branch out all k of those things, we get kb new descendants. And those kb new descendants are then sorted for their maximum score. So then we then pick the top k. So the overall cost of the sort is kb times log kb, which is right here. And we do that n times because we have to assign n variables. So that explains that order complexity. And you can think of beam search as giving you the ability to sort of do a trade-off between efficiency and accuracy. So if you set k equal to 1, then you just get greedy search, and it's extremely efficient because your computation is linear in the number of variables. You just pick a variable, assign it, pick another variable, assign it until you've completed. And if you set k to be extremely large, then you end up exploring the entire tree, and that becomes exponential time. So it gives you a knob that lets you go between linear and exponential time in the search. Yeah, question?
What happens if there's a tie? So k equals 2, and it finds 3 paths with weight 3?
Yeah.
Like, how does it pick?
Right, okay, so the question is what happens when you're doing beam search and multiple configurations have the same score, and in fact, there are more configurations with the same score than you can keep on the beam. And this is more just an implementation detail. Sometimes people just randomly pick k of them that have the same score. Sometimes you just pick the k that are best under some other heuristic. There's nothing really formally defined about it. The whole procedure is kind of approximate anyway, so there's no guarantees. Okay, I'm gonna speed ahead a little bit because we're running slightly behind. Okay, so now we're going to talk about a different way of satisfying or setting all the variables to particular values. This one is going to be called local search, and I'll explain why it's called that in a second. So in backtracking and beam search, you can think of building up the assignments of variables as a very incremental process where at first you have nothing built, and then you assign some things until you've completed your entire structure. In local search, we'll think about having an already complete structure and making a few changes to it. So you're not building this house kind of from the ground up, but you're just taking the door out and putting a different door in. Let's see how that works. Okay, so the algorithm for local search is going to be called iterated conditional modes, and I'll explain why it has that name in a second. But let's look at this factor graph that we've been working with the whole time. So the current assignment is 0, 0, 1. Now, you might look at that and say, well, is it possible for me to change just a single variable so that I get a higher score? Just one variable. And for this particular factor graph, it turns out that, yes, you can. So let's say I hold x1 fixed and I hold x3 fixed. So x1 is always going to be 0, and x3 is always going to be 1, as in the original assignment. But I'm going to change the value of x2 to be one of these values for v, 0, 1, or 2. And if I just plug in these different values and compute the weight of the factor graph, I'll see that this assignment right here, where I set x2 to equal 1, actually gets me a better value of 4. So the algorithm is just, OK, change one variable, see if I can do better, and then set that variable to the new value. Once I've done that, pick another variable, see if I can locally change it to be better, and keep going. So the reason this algorithm has this name is because we're iteratively updating a single node. And what is the conditional in this name? So conditional means under the condition that I hold everything else fixed, let me optimize one of the variables. And then the mode part is just saying find the maximum value for this node that I'm changing. So that's where you get that name from. OK, now we have a new assignment, which is 0, 1, 1. And we can keep doing this on different variables. Another important thing to note about this algorithm is that when you change the value of a single variable, as described, the algorithm says you have to recompute the entire score or weight of the entire factor graph. But if you look at the formula for the weight of the factor graph, when I change the variable x2, only these red factors change. In other words, only the factors that are touching x2 actually need to be updated. And this is very computationally good, because when I change a single variable, I only need to recompute the 3 factors touching that variable. I don't need to recompute the rest, which will give us big savings. OK, and that's why it's called local search, because you only need to look at a local part of the graph to do this optimization. All right, so formally, first you just initialize all of the variables to random values, and then you go through each variable incrementally and pick a better value for each variable, holding the rest fixed. And you keep doing this until none of the variables change anymore. That's the iterated conditional modes algorithm. And here's just a diagram showing that. So at every time step, I'm updating the one that's in white. OK. I think we've got actually a little bit of time to see how this works. All right, so this is the same graph we've been working with throughout the slides all along. Let's look at how iterated conditional modes works out for us. Step 1. All right, so the first thing that we did was we randomly initialized the variables for x1, x2, and x3. And this table down here is saying, OK, we're going to maximize x1, holding everything else fixed. And we only need to think about the 2 factors that are touching x1, so O1 and T2. We've got the values of those factors in each of those columns, and the overall weight is over here. So here we have a tie. You'll notice that assigning x1 to both 0 and 1 gives you a weight of 2. So we'll just randomly pick one. In this case, it turns out the algorithm picks x1 equals 0. All right, now let's take another step. This time we're maximizing x2. And again, you'll see that of the various options for x2, the only one, or the largest weight one, is setting x2 equals 1, and so on and so forth. So now we're optimizing x3. And we can keep going through this process, visiting each of the variables. The variable that we're visiting is in gray right here. And you'll see that as we loop through them, nothing is changing anymore. So we've reached some sort of local optimum. And you'll notice that this particular assignment actually only gets you a score of 4. But previously, we actually saw that there was an assignment that would give you a score of 8. So this thing can definitely get stuck. All right. I think I said everything on that slide here. Great. So because of the tendency for ICM to get stuck, one alternative you could consider is adding some amount of randomization into the algorithm to see if you can actually, through random changes, break out of that local optimum. And that's what Gibbs sampling is going to do. So the key idea here is rather than picking a variable and setting it to the value that maximizes the weight of the factor graph, we're instead going to randomly pick a value. But the randomness is still going to favor the values that score higher rather than the values that score lower. OK, so formally, this is what that looks like. Let's say we're assigning x2, holding all of the other variables fixed. In this particular factor graph, setting x2 to 0 gives us a weight of 1. Setting x2 to 1 gives us a weight of 2. And setting it to 2 gives us a weight of 2. So in the ICM algorithm, we would just pick one of these two because they're higher scoring. But in Gibbs sampling, what we'll do is we'll sum these numbers up, which equals 5, and then divide all of them by 5, which gives us probabilities now. And now we'll sample a value according to this probability distribution. Any questions about that, as well as questions about ICM?
So will that kind of downplay not choosing an optimal path at the beginning, but choosing one that turns out later to be optimal? Because it has a higher probability, but then you don't discard it totally, right?
Yeah. So the question is, does this help us solve the problem of referring back to the beam search? Like, if you picked something that didn't look optimal in the beginning but became optimal later, is Gibbs sampling going to be able to find it now? So there are a couple of differences. One is that there's no longer a fixed ordering in which we're building out the tree. We're just incrementally changing individual things. But you're right that this allows us to pick things that appear suboptimal with some probability. It's lower, but we still have the chance to do it. And once we've picked something less optimal for x2, we can actually potentially find another variable that does better when in combination with it. Yeah?
Because we've added in this randomness, is there any guarantee that it'll ever converge at something?
Yeah. So the question is, because it's random now, will it ever converge or reach some fixed point that will no longer change? And the answer is no. It will keep changing. But what's interesting is that if you look at all of the configurations sampled from going through this process, those actually follow a distribution that we can describe. And that actually Percy will cover in another lecture. Yeah. OK, one more question.
Is the idea of this to run this like multiple times and find the best one?
Yeah, so is the idea of this to run this multiple times and find the best one? Yes, so you basically keep doing this Gibbs sampling. And every time you sample, you get a new configuration. You keep track of how big the weight is. And if it's the biggest weight you've seen so far, then you just remember that. And you keep going, and over the course of time, the best thing you see is the thing you keep. All right. Quick demo of that. OK, so I won't go over all of these tables again. This table here, OK, maybe I should, because this will make it clear. So we've got a particular factor. This time we're updating x1. And again, the only factors that x1 is involved in is O1 and T2. So we take the product of these factors to get the overall weight that we obtain when setting x1 equal to 0, 1, and 2. So the weights are 2, 2, and 0. And that means we can sample 0 with probability 0.5 and 1 with probability 0.5. We go ahead and do that. Then we do it for x2, and we keep sampling. OK, so now there's this table down here that I haven't explained yet. So this table is keeping track of the number of times that we saw a particular configuration in Gibbs sampling. So we saw this configuration 1, 2, 2, 7 times. And we saw this configuration 1, 1, 2, 1 time. And if we keep doing this, you might notice that this distribution here will eventually stabilize. So as I keep sampling, this distribution will converge to some meaningful thing. And you'll find that actually the highest scoring configuration is also the most seen configuration in this distribution. And that has implications that are very important, which Percy, I think, will talk about once we get to kind of probabilistic graphical models. question over there.
Yeah, I'm not really clear about what you mean when you say that you're sampling.
Okay, so what do I mean when I say sampling? So with the Gibbs sampling algorithm, right, we have a fixed configuration of variables, and we pick one variable, and we randomly change its value, right? So that gives us a whole new configuration with one thing changed. We'll treat that new configuration as one sample. When we modify it again, that new thing is a new sample. So each iteration of the algorithm is one sample. And this table keeps track of what we've seen as we're incrementally mutating the structure. Yeah. Other questions? OK, cool. So that's Gibbs sampling. I think the formal procedure doesn't really need another explanation here. So this has the ability to escape from local optima, but not always. Also, its ability to escape from local optima can actually be quite slow. So here's an example of why this might not work out so well. So the example that other people have shown me is, suppose you have two people, let's say person X and person Y, and they're deciding what restaurant to go to. So maybe the two restaurants are vegetarian and steakhouse or something. So let's say, so the possible options are that X says, I want to eat vegetarian, and Y says, I want to eat vegetarian. Or maybe X says, I want vegetarian, Y says steakhouse, and so on and so forth. So these are the four possibilities of what they want to eat, right? Now let's suppose that these are two people who actually really like vegetarian food. So maybe this is 100. And maybe they really hate disagreeing with each other. So they really do not like disagreeing. And then steakhouse, oh, I did vegetarian twice. OK, maybe steakhouse is like 50. OK, so if they start out, if we initialize them to both saying that they like steak, OK, now let's try to change Y's opinion, right? So if I hold X fixed saying steak, then Y will say, oh, well, I really don't like disagreeing, so I'm going to stick with steak, right? Then we say, OK, let's update X. Well, now we're looking at these two rows, or now we're looking at, so Y we said is fixed to steakhouse. So we're looking at these two rows right here. And again, X says, oh, I really don't want to disagree with Y, so I'm going to stick with steakhouse. So even though they both love vegetarian food, they're stuck in this local optima where they keep proposing, oh, let's do vegetarian because you want that, right? That's kind of the problem you can get stuck in with Gibbs sampling. OK, so quick quiz, just to see if people are still here. So which of the following algorithms are guaranteed to find the maximum weight assignment? And these are the options. Let me go ahead and reset this. And I'll give you guys a few seconds to think about that. Oh, activate, sorry. OK. Oh, maybe my access to the network is actually not too great. OK, I'm going to have people think about this, and then I'll just give the answer. OK, cool. So the answer is that backtracking search will find the optimum, but none of these others will actually is guaranteed to find the optimum, not even Gibbs sampling. So you might think, well, with Gibbs sampling, at least maybe there's some tiny probability that I'll find the answer. But that's not actually true either. So in this example that I just gave, if I had set these two values to 0, then you'll notice that once I've gotten into this state right here, there's 0 probability of the other person changing their opinion. So even that won't find the overall optimal solution. OK, so let's have a quick summary of what we've done so far. We've looked at 2 different ways to find maximum weight assignments. The first is this incremental procedure where we build up the assignments. And we've got backtracking search, which is exact but takes a long time. We have beam search, which is approximate but is quick. It's linear. And then we have these local search procedures where we take a complete assignment and modify a local part of it. And for that, we saw ICM, which is deterministic, and Gibbs sampling, which is like its randomized version of ICM. So that covers the first part, which is sort of describes all the different search procedures you can use to find a maximum weight assignment. What we're going to do next is not look at search procedures, but actually look at ways of changing the structure of the graph so that it's easier to find maximum weight assignments. And these two parts, I think, are actually really interesting, and they come up a lot in machine learning and artificial intelligence, so hopefully I can do these two parts justice. All right. So as I already mentioned, the key idea here is to somehow change the shape of the graph so that finding the best assignment is easier. We're going to work with this example with Australia and the nodes there to make this clear. So we already said that backtracking search takes an exponential amount of time in the number of variables. You saw that it was cardinality of the domain to the n, where n is the number of variables. But let's look at this graph right here. So in this graph, all of the variables are not connected to each other. They have a unary factor coming off of them, right? So the weight of this graph is just the product of these individual factors. So if I wanted to optimize this, one thing I could do is, let's say each variable can take on 2 values. One thing I could do is try all 2 to the 4 combinations of these variables and just figure out which one has the highest. But there's a much simpler and easier way to find the maximum value assignment for this factor graph. Does anybody want to suggest what that might be? Okay, over there.
The optimum for each one.
Okay, yeah, so the answer is just find the optimum for each one. So why is that? Let's write out this graph and see how that might work out. Okay, so I'll do it just for 2 variables, just to keep this simple. Let's say you have x1 and x2. And you've got a factor for x1 that says, let's say they can take on 3 values, a, b, and c. Maybe this is 10, this is 2, this is 3. And then x2 can also take on 3 values, a, b, and c. Maybe this is 11, 4, 0. Okay, so if I just look at x1, it looks like b is a pretty good option because b is bigger, right? Because there are no factors connecting x1 and x2, no matter what x2 does, b is the best option. If x2 picks, a, there's no reason for me to pick the other ones because when I multiply that by the other one, I'm just going to get a smaller number. So the key idea here is that if a variable is separated from other variables, you can just optimize it all by itself. And that's really a very nice condition. So if you think about this, this would have been 2 to the 4 if we just did backtracking search. But now, to maximize each one separately, the amount of work we have to do is just 4 times 2. Because for each one of these variables, we just do a work of 2 to figure out which of the assignments is best. OK, so that's the idea of independence. If we take the variables in X and we partition them into 2 halves, A and B, we say that the sets A and B are independent if there's no edge between A and B. So if you're in the set of variables for A, there's no path you can take in the graph to get to the set of variables B. And that's independence. And when that happens, you can treat A and B as completely separate constraint satisfaction problems. And this will be the symbol that we'll use for indicating independence. All right, so a quick example here. This was from last lecture. You'll notice that t is not connected to the rest of the variables, and so t is independent from the rest. All right. Now the thing is, in most constraint satisfaction problems, you're not going to end up, somebody is not going to give you a graph where all the variables are separate. Usually they'll all be connected. And if you look at this graph here, you'll see that nothing is independent. But at the same time, it kind of feels like they're almost independent, right? Like if I were able to just get rid of x1, then there would be no path between any of the remaining variables. And that's what we're going to try and achieve with the 2 tricks that we'll see today, conditioning and elimination. Cool. So let me first explain what conditioning is, and then we'll see how to break a graph down using conditioning. So we'll start with just 2 variables, x1 and x2. And this is the factor relating those 2 variables. So suppose I told you that x2 is definitely blue. I know x2 is blue, just trust me. In that case, let me write this one out. So what have we got here? RR, RB, 1732. And then we have BR and BB. Okay. Okay. So if I told you that the value of x2 is blue, then immediately you can say, all right, well, that's good. I don't need to look at this row anymore because this row has x2 equals red. And I don't need to look at this row anymore because that also has x2 equals red. Right? Now the factor looks like this if I've set x2 equals b. And at the same time, because this column is just all b, I can just remove this column as well. So what do we have now? Now we actually have a new factor which only depends on x1, r and b, and the value that it corresponds to is just the value of what this original factor would have been if x2 is b. So that's what conditioning is. Conditioning allows you to delete a variable and replace it with a new factor that is the original factor but with the deleted variable plugged in. Any questions about that? Or, if this is confusing and doesn't make sense, just say like, this is confusing, tell me again. Okay, so that's the key idea with conditioning is you basically fix the value of some variables, which allows you to then delete the variable from the graph and replace it with new factors. Okay, and let me just go through this notation here. So f was the original factor that took two variables, and now I've removed its dependence on x2 by just plugging b here. And we'll define a new function g, which no longer depends on x2, and it implicitly has b applied to it all the time. All right, so now let's go back to the map of Australia, and let's condition on two variables. So we'll condition on q being red and SA being green. So if we apply the conditioning operator that I just described, the resulting graph looks like this. So there was a slight jump from looking at two variables to looking at this more complicated graph. So exactly what happened here? What you can see is that every one of the original factors connecting SA, those factors are still here. This one is here, this one is here, this one is here. And the factors connecting Q are also still here, with the exception of the factor that was connecting SA and Q. Notice that that one is no longer in the graph at all, but the rest are still there. So the reason the one connecting SA and Q is gone is because both values that go into that factor are fixed. So there's really no function anymore. It just takes on a single value. And so now we have a graph. All the remaining factors that still have variables connected to them, they're still there. But the key idea now is that these two things are separate. So I can optimize WA and NT by itself, and then I can optimize V and NSW by itself. And that gives us sort of large savings. OK. So if you remember the original factors that were in this problem, basically the new factors are saying, in this new graph, all it's saying is, well, NT can't be red, NSW can't be red, and then these guys can't be green, conditioned on me setting Q to red and SA to green. This is basically a picture of the same idea. So hopefully if I just show you another graph, we can see that again. So we're removing xi because we're setting a value to it. And all of the factors that touched xi, f1, f2, and f3, these all get updated into new factors that are now dependent on one less variable. But the same factors are still there. They've just had the value of x1 plugged into them. And this gives you maybe, for people who prefer the formal notation, we've got a variable xi. We're going to set it, we're going to fix it to some value v. And then we're going to look at all the factors that are connected to xi and remove those. So here the notation is that we remove them and put them back as these new factors, g sub j. But I guess you can internally think of it as those factors are still there. We've just plugged in a constant value. Cool. So now we can talk about this notion of conditional independence. Suppose you have a set of variables A, B, and C, which I'll put up here. So maybe you've got something like A, B, and C. And we say that A and B are conditionally independent given C if conditioning on C produces a graph in which A and B are independent. So let's say C looks like this, and then we've got a factor here to A and a factor here to B. And if we remove C, then A and B become independent. Okay. So for this problem of the sort of map coloring problem in Australia, you can see that if we condition on the grayed out variables, we can break the graph like this. And this is a formal statement of what I just said. So the part that we're conditioning on usually goes right here on the right of the pipes. And the independent components are this part right here and this part right here. Okay, so suppose we wanted to actually separate other variables from the rest of the graph. Say I wanted to separate V from all the other variables and make it a standalone island. The way I would do that is I would condition on SA and NSW. If I did that, V would be separate from everyone else. And likewise, if I wanted to separate WA and NT, then I would condition on those grayed out variables. And this kind of leads to a more general notion, which we'll call the Markov blanket. So the Markov blanket in kind of intuitive terms is, what are the nodes you have to destroy to make a certain set of nodes an island? So the Markov blanket of A, you can define that as all the neighbors of A that are not in A, which intuitively is the boundary of everything that kind of, the minimal set of things you can use to cut off A from the rest of the world. Here's a picture of that. So there's A. The Markov blanket is C, and the rest of the variables is B. Any questions about that definition? Okay, cool. Oh, yeah.
What does it mean by that x/a or a union c?
Oh, yeah, okay. So this in set notation, this backslash, is the removal operator.
Gotcha, thank you.
Yeah, so I'm removing A union C from X. Yeah, okay. Other questions? I'm glad that you asked that. All right, cool. So let's go back to this problem of this graph that looked like it was almost independent, but not quite. So if we actually condition on the value of x1, now all of the variables below are independent. So the way to actually solve this one without actually having to enumerate over, like let's say that all of these variables can take on 2 values. Naively, it would be 2 to the 7 different combinations we'd have to consider. But a better way to approach this is to just set x1 to a particular value, let's say set it to red, and then find the solution for all the remaining variables. And then set x1 to blue and find the solution for all the remaining variables. So now you've actually covered all the different scenarios, and you just pick the best one from that. And that's a lot cheaper, right? Because once you've set x1 to a particular value, each of those problems becomes independent. And so if there are 6 variables down there, it's literally just considering doing 2 operations for each variable. So it's 6 times 2. And then for x1, you just have to flip it from blue to red. Oh, there's green too, but same idea. OK, cool. So a summary of this part of the lecture so far is that when you can take sets of variables and disconnect them, you can solve the problems independently. And conditioning is a way to actually break the graph up into discrete parts. Once you condition, of course, you can't just leave that variable fixed. You have to try all values of the variable that you condition on and solve the remaining problems for each of the values if you actually want to find an optimal solution. Okay, and this idea of conditional independence is the following. So C is a variable that blocks all paths between A and B. And if you condition on C, then you've essentially blocked all the roads between A and B, and they become independent problems. And the Markov blanket basically gives you a definition of what roads you need to block in order to make a set of things independent from everything else. All right, so now we're going to save the last part of the lecture for elimination, which is the final idea that we have for changing the structure of the graph. Okay, so with conditioning, what we did was we took a variable and removed it from the graph completely, and then we added, or we rather modified the existing factors so that they only took a fixed value of that variable. With elimination, we're still going to remove xi from the graph, but rather than fixing xi to a single value, you can think of it as kind of roughly setting xi to the best possible value possible, so that in that case, we don't have to actually iterate over the different values of xi. So again, let's look at this from the point of view of just two variables. So this is the same factor as before, x1 and x2. And in conditioning, as we said, we only consider one value for b. And in that case, we saw that the factor reduces to this smaller factor here. With elimination, what we're going to do is we'll actually consider all different values that x2 can take. So let me put that up on the board to be more concrete. And then the value of the factor. Okay, same values again. 1, 7, 3, 2. Oh, maybe I should actually use colors. Okay, so same factor as before. And what I want to do is eliminate the variable x2 such that I don't have to think about it ever again. So what I'll do is we'll say, okay, I'm going to first think about x2's neighbor, x1. So suppose that x1 were set to red. In that case, what would the best value for x2 be? Somebody can just shout it out. Blue, okay, right? So now that I know that I'm going to set x1 as red, then blue is the best value. So I can delete this row now, because I know that if I'm only interested in the max, there's no reason to keep that row. For x1, now suppose that x1 is going to be blue. In that case, what's the best value for x2? Red, okay. So then I can delete this row. All right, so now I only have 2 rows left, but the 2 rows cover all the possible values of x1, right? We've got both red and blue. And now what I'll say is I can drop x2 now. I don't need to think about x2 anymore because I've already optimized x2 for every possible value that x1 could have taken. So I drop this, and now we don't see x2 anymore, and we have a new factor that only depends on x1 and gives you the value of the factor. So what happened here? What happened was I'm still only giving you 2 options for x1, but the score that you get for picking this has already internally optimized the best value of x2. So that's what elimination is. It's kind of pre-computing all the possible work you could do on the eliminated variable. So in elimination, you have to pay attention to all your neighbors. You have to say, okay, I've got these neighbors, and they could take on these different values. And for each value my neighbors could take on, I'm going to find my optimal solution. And I'll pre-compute it and put it here. That's what's happening in elimination. I'll give another example very soon to hopefully solidify that. Okay, so here's an elimination that involves more than 2 variables. We've got 4 variables, and we're going to eliminate x3. So let's look at pictorially what happened here first. So pictorially, x3 had 2 factors connected to it, f13 and f34, right? After we eliminated x3, we've got a single factor, f14, that has replaced the two factors coming out of x3. And in elimination, that's what is always going to happen. What's always going to happen is that the variable you eliminate, you look at all the factors that it's connected to, and you merge them into one big factor. And that big factor will be connected to all of the neighbors that you could directly reach from the variable that you eliminated. And perhaps intuitively this makes sense, because what we're doing in elimination is we're paying attention to all of the neighbors of x3, and we're saying, I need to compute a factor that gives me the best case scenario depending on any sort of combination of all my neighbors. So the resulting factor still has to be connected to all of those neighbors. If it's not connected to one of those neighbors, then there's no way to know whether we're giving the optimal value dependent on those neighbors. OK, so formally, let's see what's happening here. So what is F14? F14 is connected to x1 and x4. And what it's saying is, OK, for any particular value of x1 and x4, the new value for this new factor is what we would have gotten if we maximized over all possible values of the deleted variable x3. So that's the max over here. We're maximizing over it. And this quantity in here, this is the product of all the original factors that were connected to x3. So they're still implicitly there, but they're in the definition of F14 now. Any questions about that? OK. And this is how the process actually works out in sort of concrete numbers. So these were the two original factors that were connected to x3. And they took in these values for x1 and x3. And we got these scores. So what we'll do is we'll take the product along each row to get new numbers, which look like this. Let's see if I can say anything else about this that makes it more clear. Yeah, I don't think that this diagram is going to give any more intuition on this. OK, cool. So the overall picture of what's happening here with elimination is that we remove a variable, and we take all of the factors that are connected to that variable and merge them into a single factor, which is what you see here on the right. And here's a more formal definition of what's happening. So again, you look at all of the factors that depend on xi, remove them from the graph, and then add a new factor which implicitly maximizes over the variable that you removed. OK. And maybe one final point to note is that the scope of this new factor is the Markov blanket of the variable that you removed. So if you recall, the Markov blanket is everything that's immediately touching that variable. All right, so another quick question. Suppose we have a star-shaped factor graph. So you've got a factor graph that has this shape right here. You've got one variable in the middle, and many variables coming out of it, and individual factors along all of these locations. So the question is, if I were to remove this middle variable, I would like to remove this middle variable such that all the leaves of the star are now independent. And the question is, should you use elimination or conditioning to make those leaves independent? So who thinks that you should use elimination to make things independent? And who thinks that you should use conditioning to make things independent? OK, cool. That's good. Yes, so it is conditioning. What elimination would do in this scenario is all of these factors right here would disappear, and we would have a single giant factor that connects all of the variables. That's what would happen in that case. OK. Now let's actually work through one more example of elimination just to kind of solidify this a little bit further. So suppose we had 3 variables. Let's call them x, y, and z. And we're going to look at the worst kind of factor graph possible, which is that all of the variables are connected to each other through one factor. So there's really not much sort of independent structure in this problem. And there's going to be one factor. And let's say that the factor is constructed like this. So each variable can take on 2 values, either a or b. And I'm going to do out the whole thing for a second here. A, B, B. B, A, B, A, B. B, B, A. And finally B, B, B. OK, so this is the entire factor. And let me just assign some scores to it. So just to keep this simple, we'll say that the factor weights are 1, 2, 3, 4, 5, 6, 7, 8. So it's pretty obvious here that the best configuration is the bottom one, just because of the way that I've done it. But this is really a bad factor, because it's growing exponentially in the number of variables, right? Each variable takes 2 values. There are 3 of them. There are 2 to the 3 different combinations. This is bad. So how would variable elimination work on this giant factor? Let's suppose that we started by eliminating variable z as our example. So to do that, this is how you can think about it. So z is connected to both x and y. So we need to consider all the different combinations of values that x and y can take on. So the first consideration is that x and y could both be a. That's represented by this block here, right? And clearly, the best value for z is to be set to b. So having figured that out, I'm going to go ahead and delete this row. All right? The next configuration that x and y could be in is that it could be x could be a and y could be b. So that's these 2 rows right here. And again, the best configuration for z is b here, because that's 4. So again, I'll delete this row because we know that it doesn't matter anymore. And I'll keep doing that for the remaining ones. So the other configuration that x and y could be in is BA. Again, this row can go away. And finally, there's the configuration where both x and y are b. And this row is suboptimal, so I'll remove that. All right. And now I can remove the entire column B entirely. Sorry, the entire column for z. So we're left with this. And our factor graph now looks like this, because we can remove z. If I do this again, this time I'll eliminate y. So to eliminate y, I need to think about the different values that x can be. X can be either a, or it can be part of b, right? So the best value when x is a is when y equals b. So again, I remove this row right here. And now looking at the 2 rows where x equals b, I see that it's better for y to equal b to get 8. So again, I remove this row right here. Now I don't need to think about y anymore. So I can remove y as well. And now we've just got x can be a or b. right? And now, if I want to find the optimal weight to this thing, well, it's just b, and that's 8. So that's how we can, so basically you can take any factor graph and eliminate one variable at a time until you only have one variable left, and that variable will give you the solution. You just look at its values and you get the solution. So that's a new algorithm for actually finding the maximum weight assignment. And now you could say, well, I've got the maximum weight, but I didn't actually get the assignments for what all the other variables should be. I only know that x should be b, and that's it. But if you run this algorithm backwards, you can say, all right, well, I know that x is b now. So I can go back to the previous step. So in the previous table, I had more values, right? I can plug x equals b in there, and I'll get another table where the optimal value of x is known. And then from there, a few rows will have been removed, and I can recover the best value for y. And once I know y, I can plug that into the earlier table that I had. And you can keep plugging those values backwards into the earlier tables that you constructed and find the best value of the thing that you removed at that step. So by going backwards through this process, you can recover the optimal assignment for each variable. Any questions about that? Yeah.
Isn't that just backtracking search? I mean, you're going to be searching exponentially, right?
Oh, so why is there no exponential blowup on the way back is the question. It's because you've conditioned on the optimal value of the variable that you just figured out. Yeah. Maybe after class I can try and work out another example that's more clear. Yeah. But at the very least, you should see that by eliminating, you can get to an optimal weight using this approach. Okay, so with your remaining time, I want to talk quickly about the actual order complexity of this algorithm. So you'll notice that in the procedure that we just went through, let's go back to, so in the original table that we had, that had x, y, and z here, with all of the values that were filled in here, we had to actually look through every single row in this thing. And for each of these rows, let's see, so how many values were there in this factor? There were n values, which is the number of variables. That's the number of rows in here. And the number of, So the domain is this cardinality right here. And the number of variables in this factor, let's call that max arity. So recall that the arity is the number of variables that go into a factor. This is the number of rows inside this factor. And when we do variable elimination, we actually have to look through all the rows, as you remember, to eliminate a certain variable. So intuitively, you can see that the order complexity of eliminating a variable from a particular factor is going to be roughly on this order. And if you have a graph that has a bunch of different factors in it, let's say you've got, maybe you've got a factor here, and then you've got some more factors here. Let's call this like k or something. This one has two things in it, right? So if d is the cardinality of the domain, this is d to the 2, and this one here is d to the 3, right? So d to the 3 dominates d to the 2. So really, the runtime of eliminating all the variables is going to be dependent on the factor that has the largest arity, right? Because it's really this exponent up here that gets you. So the overall order complexity of variable elimination is just the domain to the maximum arity factor you encounter as you're doing this elimination. Oh, and there's an extra end there because you actually have to run through all of the variables. Okay, so what is the actual maximum arity factor that you encounter when you're doing variable elimination? And what we're referring to here is as you eliminate variables, each factor is one of these squares, and the number of edges coming out of it is its arity. So you want to eliminate variables in a way that leaves you with factors that don't have a high arity, because the higher the arity, the more complexity it takes to eliminate a variable from that factor. So for this graph, for example, if you eliminate each of the leaves one at a time, you never end up with a factor that is larger than 1. So if I eliminate, say, x2, that creates a new factor hanging off of x1, where x2 would have been. And as I eliminate all the leaves, then I only have a factor with arity 1 all along the way. But if you eliminate x1 first, then you end up with a factor that's tying together all of the variables. And then you end up with a very expensive operation. So depending on the order in which you eliminate variables, you will get a very different runtime. And what people do as a heuristic is they tend to eliminate the variables with the fewest neighbors first. All right, I'm going to try to quickly go through this since I know that class is pretty much up. A key definition here is the tree width. So the tree width of a given factor graph is the maximum arity of any factor created by variable elimination with the best variable ordering. In other words, the tree width tells you the best kind of complexity you can get if you eliminate variables in the best way possible. And it's generally very hard to compute this. It's NP-complete to actually compute the best ordering. But for certain well-known structures, it's fairly straightforward. So for a chain, you can imagine like just a sequence of variables laid out in this way. You can eliminate from one side to the other, and the tree width will, or the arity of the factors will always be 1. So that's the tree width. For a tree, it's also 1 if you just eliminate from the leaves. For a cycle, it's 2. You can probably do this exercise for yourself. And for a grid, it's going to be, so if you have an n by n grid that has factors of the following shape. So if this is your factor graph, and it's m on this side and n on this side, it will be the smaller of the two. And that's something that I'll just leave as an exercise. So cool, we're now down to the last slide. Thanks for your patience. So we've looked at a few different techniques now. Beam search is an approach for finding an optimal assignment to variables that's approximate. We essentially search over different assignments. Local search is an approach where we start with a complete assignment and then tweak individual variables, holding the rest fixed. Conditioning and elimination are the two different ways we can use to actually change the structure of the graph. Remember that both of them actually delete variables from the graph, with the key difference being that conditioning kind of actually separates all of the variables that are connected to it, whereas elimination actually ties them together. All right, cool, thanks. I'll see you guys in a few more weeks.